talked about the challenges of the space environment and the different phases of space mission design in the previous video. Now, we're going to explore the invisible forces that govern everything we send into space, which is orbital mechanics. This is the fundamental science and mathematics that dictate how a satellite stays up, how we reach other planets, and why every spacecraft has to follow a specified orbits. At the heart of orbital mechanics are the laws discovered by Sir Isaac Newton and Johannes Kepler. Newton's law of gravitation states that every particle in this universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Simply put, the more massive the objects are and the closer they are, the stronger the pull. This force is what keeps satellites from flying off into space and what makes planets orbit the stars. Building on that, Kepler's laws of planetary motion describe how objects move under this gravitational influence. Kepler's first law states that all planets move in elliptical orbits, with the Sun at one of the two forces. This means orbits aren't perfect circles. In real life, they're mostly elliptical. For a satellite around Earth is at one focus of that ellipse. Kepler's second law says that a line joining a planet and the Sun sweeps out equal areas during equal intervals of time. This means that objects in orbit move faster when they're closer to the central body, like the Earth or the Sun, and slower when they're farther away. Kepler's third law provides a direct mathematical relationship between the size of an orbit and the time it takes to complete one revolution. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. For engineers, this is important for predicting how long a spacecraft will take to orbit. To precisely describe any orbit, we use a set of 6 numbers called orbital elements. These tell us about the orbit's shape, size, and orientation in space. The semi-major axis defines the size of the elliptical orbit, so a larger semi-major axis means a larger orbit. Eccentricity describes the shape of the ellipse, and eccentricity of 0 means a perfect circle, and as eccentricity increases, this ellipse becomes more flattened. Inclination is the angle of the orbit that it is making with the Earth's equator. A 0-degree inclination means the satellite orbits directly over the equator, while a 90-degree inclination means it passes over the poles, which we know as polar orbits. The remaining 3 elements, which are right ascension of ascending node, argument of perigee, and true anomaly, describe the orbit's specific orientation and the satellite's position within it at a given time. Together, these 6 numbers allow engineers to predict a spacecraft's exact location at any moment in the future. Engineers choose specific orbit types based on the mission's objectives. Each orbit offers unique advantages and disadvantages. Let's start with LEO, low Earth orbit. LEO typically is between 160 and 2000 kilometers above the surface of the Earth, and this is where satellites travel very fast, completing an orbit in about 90 minutes. LEO is ideal for Earth observation satellites, remote sensing, human spaceflight, including the International Space Station. Because these satellites are close to Earth, LEO offers this benefit of high-resolution imagery, though they have a limited view of the Earth at any single moment. Medium Earth orbit ranges from 2,000 kilometers to about 35,000 kilometers from the surface of the Earth and is mostly famous because of its use by global navigation satellite systems, GNSS, like the GPS. Satellites in MEO orbit the Earth in usually elliptical orbits and provide a balance between global coverage and orbital period. A constellation of MEO satellites can provide continuous global coverage, which is essential for accurate positioning and timing. Geostationary Earth orbit, or GEO, is the one that is located at 35,786 kilometers above the Earth's surface. It's important to notice that the altitudes mentioned in this video are the distances from the Earth's surface and not from the center of the Earth. Satellites in GEO orbit Earth at the same rate as Earth's rotation, meaning they appear to remain stationary above a single point on Earth. This is why GEO is perfect for communication satellites and several other important everyday applications. The downside is that the high altitude means a significant cost of communication and a large launch energy requirement. Highly elliptical orbits have a very elongated oval shape. A satellite in HEO moves very quickly when close to Earth and very slowly when far away, following Kepler's laws. This slow movement at apogee, which is the farthest point in an orbit allows for long observation periods over high latitude regions, which are not always well covered by GEO satellites. The Molniya orbit is a prime example used for communications over polar regions. While objects naturally follow their established orbits, engineers often need to change these paths. This requires orbital maneuvers, which involve firing thrusters to change a spacecraft's velocity, characterized primarily by delta V. Delta V is a key metric in space mission design, representing the total change in velocity a spacecraft can achieve with its propellant. One of the most common and fuel-efficient maneuvers is the Hohmann transfer. This maneuver is used to move between two circular orbits in the same plane. It involves two engine burns, one to enter an elliptical transfer orbit and a second burn at the farthest point of that ellipse to circularize the new higher orbit. This is a standard way to send probes from low Earth orbit to higher orbits or even to other planets sometimes. Another common maneuver is an inclination change, which alters the angle of the orbit relative to the equator. This is typically fuel intensive, especially for large changes. Orbital maneuvers are critical for everything from reaching the correct operational orbit after launch, performing station keeping to maintaining a satellite's position, to avoiding space debris and eventually deorbiting a spacecraft at the end of its life. Orbital mechanics provides the blueprint for cosmic navigation. By understanding these fundamental laws and engineering smart maneuvers, we can precisely place and control a spacecraft, enabling everything from global communication to deep space exploration. This is therefore one of the most essential pillars of space engineering. If you are technically inclined, I've published a mini guidebook on spacecraft navigation that you will find helpful to study along with this video. You can find the link to the guidebook in the description. In our next video, we will break down the spacecraft subsystems. So stay subscribed to this channel and keep learning.